Alright, so are we live? Hello, hello, welcome. Got another problem here to work on, and just give it a moment or two. Check something out here. Yeah, I kind of just want to bang out some problems, do a bunch. Rather enjoy this. I'm trying to decide whether or not I want to exercise today. I have the opportunity to exercise. Like, there's a gym here. There's an erg rowing machine. I'm tempted to go down there and do a rowing exercise. Yeah, I've been very hesitant about exercising because I was really stressed out about a bunch of stuff. And I was like, maybe I'll just slow down. I basically didn't want to hurt myself before. I was going to move a whole bunch of things. I don't want to hurt myself, but it's like, like if I over exercise and I'm too sore, and then I try to move something heavy and I hurt myself, that kind of thing. Your knees are kind of weakened when you're sore. You don't want to overdo it. But all my plans are kind of just like all over the place now, so I'm like, freaking whatever. Just calm down, relax, take it slow, take it step at a time. It's not rushing, you get into so many problems just by rushing things. Take it slow. But anyway, I might do that later today. I don't know. But here, this problem is an interesting one. It is yet another question. Let's see how it goes. I'm gonna move this closer, So I'm not always like searching for it. Because I keep doing that. I got all these scenes, so yeah, normal full screen. Just keep it real simple. All right. Okay. H-index. Let's go. Well, that's a lot of downvotes. An array of citations. Each citation is a non-negative integer of a researcher. Write a function to compute the researcher's H-index. According to the definition of H-index on Wikipedia, a scientist has index H if H of his or her N papers have at least H citations each, and the other N minus H papers have no more than H citations each. That's the H number, H-index. Input citation 30615, output 3, explanation 30615, means the researcher has 5 papers in total, and each of them had received 30615 citations respectively. Since the researcher has 3 papers with at least 3, so 1, 2, 3 citations each, and the remaining 2 with no more than 3 citations each, her H-index is 3. Okay, so it's kind of like a midpoint. It's H of the papers have at least H citations, and the other N minus H have no more than H. Oh, that's interesting. I think it's possible. I don't think every array will have an H number. Like doesn't always, like this definition isn't true, doesn't exist. Like every array doesn't have an H number by this definition, if that makes sense. In other words, you could have there's N and H. Oh wait, no. Am I wrong? Wait. Non-negative integer. Like if you have 0, if all of your, I'm just thinking, how do we express this? I'm just trying to think of an example where no such H exists, where this is true, where Wait, I'm so confused. Each of the papers have H citations, right? So, and then the other ones have no more than H. Yeah, that's like really confusing. Like if you had all of your papers had 0 citations, then you can't have H greater than 0 because none of the papers have 1 citation each at least, or 2 citations each. So you can't. So it has to be at most 0, but it can't even be 0 because no more than H. Well, it could be equal to 0. Okay, so actually 0 works if they're all zeros. Let's say you have 1 with 1 with 1. Then you have okay, all right. I mean, maybe it makes sense. I don't know. I'm kind of struggling to understand. So H of the papers have at least H citations, and all the other papers have no more than H, have less than H. Okay, no, I think it works. I think it exists. It's just a weird definition, but I think I get it. So if you have one paper that has at least 1 citation, your H is at least 1 because everything else is less than that, and that's fine. If you have 2 papers with 1, it's still just 1 because everything else is less than 1 or less. If you have 1 paper with 1 and a paper with 2, it's still 1. No, see, there you go. Right, see, that's a problem. Right, if you had 0, 1, 2, 0, 0, 0, right? If you have at least 1 paper with 1 citation, and all the other papers have no more than 1, that's not an H. You don't have an H index of 1. In other words, yes, that's what I'm saying. Like, this is such a confusing definition. Several possible values for H to the maximum. Right. So let me show with that. What about this? Like, what is this definition? Saying, yeah. I'm not crazy, right? I'm not crazy. This is definitely 3 and 0. Okay. If you put 1 in there, you should get a 1. If you put, obviously I'm using their, fortunately we can use their code running tool here, this test case tool, to find out what's expected. 1. Okay. See, this is what I'm saying. This doesn't make sense, right? Because each of the papers have at least H citations. So 1 paper has at least 1 citation, true. And the other papers have no more than H each, false. The other papers have, one of these other papers has 2. So that's a very confusing definition. It's like if you put a 2 in here, or if you made all of these 1, still gives you 1. Throw a 2 in there. Two. Now if you make this a 3, it's still going to give you 2, I think. I don't really understand their definition. I actually think part of my solution to this problem is literally figuring out what they mean, because this doesn't really make sense. Yeah. kind of want to look at the hints, but so what I'm going to take this to mean is that really just drop off the other portion. Is just that if you have at least H papers with at least H H papers with H citations. So if you have 4, 4, and 4, you get, I think, 3 for that one. Yeah, that's what I think. I have to put like a bunch of different test cases because just, I don't know, it doesn't make sense to me. But in that case, it's pretty straightforward, I think. You would do, in that case, I think it's pretty straightforward. I'll tell you what I think you do. So you can just do like a I want to say a frequency map of your numbers. Yeah, so this is an interesting question. I mean, the definition being really awkward is ignoring that for a moment. What's interesting about this is it's kind of like counting areas, in that if you get 6 4 times, you get a number of 4. You have at least 4 papers with at least 4 citations, even though you have 4 with 6. And then if you had 2 more that were like 8, then you would go bump up to 6, because now you have at least 6 that are 6. So pretty interesting question. Yeah, there's a certain element to this that reminds me of basically like counting areas, something like that. Finding areas in a graph, we'll say, like a bar graph. It has a certain analog to that. It's a little bit different than that, though. So I want to say there's probably some kind of stack-based solution that we can do. So one naive approach would be to just have every integer that you see, you have like an unordered set, which you would place in that array. So an array that's sort of the size of the integer that you see, and you would add a 1 to every value in that array, right? And so each integer you see, you just sort of increment all of these values as you go. And at the end of it, once you've incremented everything, you sort of tallied everything up, then you just loop all the way through and find the largest value where the value at that index is greater than or equal to the index itself, if that makes sense. And that's it. The problem with that solution, though, is that the integers themselves could be very large. And not only that, you're not just counting each integer, you're adding, you're incrementing an array index, whatever the number is, that many times, right? So if the number is 5, you're going 0, 1, 2, 3, and 4. 0, 1, 2, actually going all the way to, you're doing even one more. You're doing 0, 1, 2, 3, 4, and 5, incrementing each of those array indices by whatever's there by 1. which is really kind of excessive. That's like really a lot. Yeah. Excuse me. So I'm not really sure though how to handle this. Well, I think if we sort the array, that helps us, right? Because then we can say, oh, that's interesting. Yeah, so if you sort the array, that helps a lot because you can figure out how many. So h is always at least 0, right? You can figure out if, because it's sorted, everything to the right is at least as large as the number that you're looking at, right? So if you look at, you see a 1, then you could say, okay, all the numbers to the right of this, including this one, the size of the array, that's obviously at least 1, but it's it's at least, you see at least, you actually, not even at least, you see really exactly that many numbers that are at least of size 1. So if that's greater than 1, boom, you can take, you can upgrade it at h to that value. Then when you see the next value, you do the same check, and so you can use the size to the right as long as it's greater than the value you're looking at. So what's left in the array is greater than or equal to the value you're looking at, right then and there. That should do it. That should solve it right then and there. So we can do ret equals 0. We'll do standard. So actually, we do want to sort this then. Well, we'll do this. Do a little extra work. I don't like to destroy. It doesn't really matter who does it. No, not really. Because it's just copying again anyway. Sort, and then we're going to say for int I equals 0, I is less than dot size, increment I, set int x equals citations of I, and we're going to say balance left is citations dot size minus 1 minus x minus I plus 1, which is just minus I. Yeah, including, that's how many, right? Okay, that's left, and we say if x is less than or equal to balance left, then we're going to say ret equals standard maximum of ret and I, or really x. And that's it. Something like this. Something like this. Wrong answer. Nice. 3010. Okay, we sorted. We said, okay, look at the value. X, the amount. We're going to say the number of values left, so So 0, 1, 2, 3, 4, 5. The size is 5 minus I is 0. If x is less than or equal to 5, which it is, then we take the maximum, a ret in x. So 0, then there's 4. 0 is less than or equal to 4. Then we say, oh, I'm sorry. Oh, that's interesting. So actually, it's not being less than or equal to. It's oh, that's interesting. So really, we should have gotten 3 here. I think it's something like this. Actually, it's a little bit. I don't know. I got it wrong, but it's close. I want to say it's something like this. I actually don't know what we do here. Oh, that's accepted. Okay, but it's not supposed to be accepted for just that case. What happens? So you see 4 and you say, okay, if that value that we're looking at, so that value and everything to the right of it is going to be greater than or equal to that value. If that is larger, right. So depending on which if you consider those two numbers, the number of values left, if that is bigger than sort of the number you're already looking at, and then no. How do you do this? So it's okay. It's confusing, but I took the minimum of x and the number of values left because I'm thinking if you get to a number and you have a certain number of values following that number, really it is the minimum of those two, because if this number is larger than the number of values left, then you can't do better than the number of values left at that point, because you won't get any more papers sort of that size, or you won't have enough papers of the larger size. So you're actually probably done right there. That's if the values left is smaller than the number you're looking at. If the number you're looking at is smaller than the number of values left, well then you have enough. If that number is bigger than what you're already paying attention to, right, you're going to want to use it. Now that number is also going to be you have that, you get that, you definitely will at least get that number for your H index, because you have enough papers for that number. So that's kind of interesting. So I think actually it's the minimum of these two values. It's really weird to think of it that way, but I think that's right. Let's do some other examples. Some random stuff, I don't know. We could do some degenerate cases too, but I just want to do some random things just to see. I don't know. I can't even think up all the test cases that I want to use. Can't even get to 40. I can maybe do 10. I don't know what these should be. I don't know. Let's see, how do we do? So if it's empty, we get 0. 1, 2, 3, 4. 1, 2, 3, 4. All right, I think we go for it. See how we do. Oh, got it. Sweet. Hey. Hey. Not too bad. 30 minutes. Oh boy. 30 minutes is kind of a long time. So, not terrible, but not great either. Because we did sort it first before we messed around with it. And what I'm wondering is a way to do this without sorting it. That's a good question to ask. That's a good question to ask. It's a lot easier if you sort it in terms of the logic. However, I think we can do it without sorting it. I think we can just build a frequency map. I think I got it. You ready? I think this works too. No, this doesn't work. Wrong. Wrong. Because... Nope. Nope, 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 nope. You need a kind of accumulation function. No. No, this doesn't work either. This doesn't work. No, you're gonna have to sort it anyway. More or less. Yeah, I have to sort it anyway because you need you want to know how many numbers are greater than or equal to that particular number. Yeah. That's ultimately what you want to know. How many numbers are greater than or equal to that particular number? can you do that efficiently? Can you do that in linear time for each number? Obviously, you could do that in n log n time, as you saw. You could, right? You could just sort the array, and then you know how many numbers are to the right of it. Oh, there's got to be another way. There's got to be another way. I want to say you got to be able to do this in linear time. There's got to be a way to do this in linear time. I mean, n log n time's pretty quick too, but there's got to be a way. I gotta think about it some more. How do you accumulate? How do you know how many other numbers are larger than that particular number? Well, what you can do is you could do it this way. You could suppose every number is larger. You could start with that, and then no, that doesn't work. Trying to be clever by adding everything initially and then subtracting the pieces off as they come, but that doesn't really make sense. That don't make no sense. That don't make no sense. There's gotta be another way. There's gotta be another way. How do you add these numbers together? Oh. There's gotta be another way now. There's gotta be a way out. Gotta be a way now. I don't know, man. I don't know. Let's just say I don't know. If there is a way, it's probably a clever way. I don't know it offhand. It'll take me a while to figure it out. Oh, okay. Well, that's fast enough, right? Can't really do much faster than that. Okay, we'll check the discussion and see if there's a linear approach. Bucket sort. That's not. Come on. That's clean Java. Bucket sort's still sorting, right? No sort. Using a hash table. What? What? No way. I don't believe you. Really? I feel like a dummy now if I hadn't figured this out. I was like, there's gotta be a way to do this. All right. Let n be the size. Create your vector of hash n plus 1 for each I equals 0, I less than n increment. So we're going to loop over, okay, if citations of I is greater than or equal to n, increment the hash of n. So else hash citations of I plus plus. What is this going on here? Paper equals 0. Go backwards now. Paper increment by the hash of I. Paper. I feel like this is just like another. This really does look like just a counting sort. It's effectively a counting sort. It's not really. That's what I'm seeing here. This is like a counting sort kind of a thing. What a. We don't know. We don't know that. We don't know that. Citations of I is going to be. Oh, I see. Oh, that's very clever. Oh, no kidding. Oh, man. I feel dumb now. Whatever. I'm going to lay down in shame. Let's go lay down in shame. Oh, you got to be kidding me. Really? Dude, what? Oh, no. Oh, you gotta be kidding me. Ah, no. 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 Oh. Oh. Right. So this goes back to what we were talking about the minimum. The number of papers is an absolute minimum on what the value could be. Or absolute maximum, rather, on what the value could be. So any papers that exceed the number of papers, we don't care about those numbers. So it's very easy to use a hash because we could use counting sort. Oh, that's why. So we can use bucket sort on all the numbers that are less than or equal to n, right? Because all the numbers that are greater than or equal to n we don't care about anyway. We just count those as basically whatever n is. Those just only contribute to n. So that's what he did. Oh my, come on. I just feel silly now. So you can build that frequency map and then just roll it backwards from the frequency map to get the to rewrite it as a cumulative frequency. That's really clever. I mean, I'm glad we saw that, but I feel kind of dumb now. Right. Because the problem with doing that, as I described before, the problem would be that the values of n could be very large, but actually that doesn't matter because we only care about n, all the values up to and including n, which is the number of papers, which is the size of the array. Beyond that, we don't care. Oh, man. Oh, I just feel so silly now. You gotta be kidding me. You have got to be kidding me. Yeah, I'm pretty much going to write literally the same code that he wrote. It's going to be like the same thing. There's no real... there's nothing to... okay. Yeah, alright. Oh, man. So basically, it's like a bucket sort. Yeah, it's pretty much a type of bucket sort. Okay. Okay. Let's go for it. Just call it V for vector. And we'll say citations of size. +1, actually. Yeah, +1, and all zeros. Initially, and we'll say X, and we're going to say for, I don't need this yet, so process into hash table, or into preprocess a frequency map, any value greater than n contributes only to the last element. Cannot have papers number of papers can have an H value greater than the number of papers. So yeah, citations X, you really could even just do you don't even need to do this. You could just do X is greater than or equal to citations.size. Then we say V of n plus x, otherwise V of citations of x plus. So the index will keep track of how many papers of that value we see, and then anything greater than or equal to the number of papers we have, that just gets thrown into that last bucket at the end, and then we just say from the back, which is citations.size, or really just V size -1, I greater than or equal to 0, decrement I, say yeah, actually it could just be ret, yeah. Ret plus equals V of I. No, we could do just total. Do it this way, I think. And what the minimum of the total in ret. Or no, same thing. It's the maximum of ret, and it's going to be the minimum of I and total. So yeah, just like that, I think. So you have all these papers that are large, some papers that are larger, and you say, okay, you're going to accumulate. So you're going to read the array basically cumulatively. So you're going to accumulate as you go. Each time, basically, the total is going to be the number of papers that are greater than or equal to I, and you want the minimum of those two. If total number of papers is more than I, then that total value is a potential value to consider. If I is greater than a total number, then if I is greater than a total number, then that total number is a potential value. And then if the total number is greater than I, then I is a potential value. So you take the minimum of those two. I think just like this. We can do just. Can also make things a little easier. Did I do that right? Hey, did I get rid of all of my test cases that I had before? Hopefully not. I think I did. I don't know. Yeah, call it a cumulative frequency map now. All right, let's go for it. See what we get. Wrong. Nice. Awesome. Whoops. I probably should have tested more cases. I kind of skipped that. I was like, do we need to test more cases? It's good. Glad we got. You rock our discipline. You rock our discipline. You rock our discipline. All right, what went wrong in each of these cases? Runtime error. Oh, no kidding. Whoa. Whoa. Wow. That's astounding. Okay. Oh. By the way, this doesn't need to be. First off, let's find the error here. Okay, that one's fine. How about this? That's fine. All right. Which one caused the problem? One, two, output two, expected one. All right, so let's find. Well, we have this wrong answer, but I actually want to find the one that caused the exception. Is that this one? No. Really? One of these? Oh. This one? Yeah. Okay, that's okay. I wasn't expecting that. So we got a wrong answer and we got a runtime exception. Okay, let's focus on these two. So 2, 4, 6. We would say 0, 1, 2. So 3. We would have an array of size 3. 0, 1, 2, 3. And we're going to say so the size is 3, array is of size really 4, 0, 1, 2, 3, 4. So we can have index 3, so 0, 1, 2, and 3. And then we say if x is greater than or equal to n, which is 3, and then we do v of n, right, which should exist. Otherwise, oh, that's okay, of course. My mistake. My mistake. Okay, yeah, that's why. I guess we'll go for it again. There we go, okay. That was my error. That was my error. I should have seen that. That was from looking at the other solution, and I was like, oh, citations of something or other goes there. No, it's not. It's just x. It's just, you just count that particular. It's the yeah, you just count that particular index. You increment that index. That's it. That's simple. Super simple. Super simple. Really, really succinct. Interesting solution. Succinct solution. I really like this. That was good. I like this question. Super interesting. Glad we looked at it. Glad we took some time. Glad we looked at the other answers too. That we can get like a better idea of how it's done, how it can be done. Yeah, I knew there was something in there. Like I knew there was something, and I missed it. I missed it. Sometimes you can use counting sort if the last value. That's a very clever little thing, but the last value, if it's all those values, can basically be considered the same thing. Also, I noticed that I'm talking kind of low, but I can probably modify the gain a little bit so that way I can talk louder. Because I like, yeah, I could. It's like the middle of the day here. Like I don't think people should be sleeping right now. I mean, not that they can't, but like it's not unreasonable for me to talk loudly now. So yeah, so that's pretty interesting, dude. I can't believe I made a mistake. I made a mistake on that. I feel so silly now. But yeah, really simple. Like if you can use a simple table for this, because all of the numbers that are outside of that table, just the indices, everything that's outside of that, you can just count that all as one thing because you're never going to have enough papers to exceed that. So, oh man, I don't really like how this is described, but this really should be. I think you really should just like remove this portion entirely. Just that if H of the papers have at least H citations each, and that's H, and then it's the largest of possible H values. Yeah, if you get, yeah, right. That's, oh man, I can't get over it. It's like such a clever thing. I missed it. Missed it. All I had to do is, yeah, just consider it's bounded, so all the numbers larger, you just throw them in one spot, and everything else follows that very nicely. And then you just consider the array as like you cumulatively consider it cumulatively. Man, got a lot of downvotes too. It's super interesting. Wow. That's an interesting question. I like that one. Super clever. All right, let me go. End that one there. Thanks for watching, and yeah, we'll turn off the stream, take a small break, and then get into another problem.